7, questions 1 to 7 for homework last night. We'll go over all 7 of those questions. There was a little bit of confusion last night as to exactly what the instructions were for these. When it says add the following vectors together, we have to not just add 20 and 10, let's say, to get 30, or not just say, oh, the x component is 20 and the y component is 10. We have to actually resolve those. We have to actually make a right-angled triangle and find the hypotenuse of that right-angled triangle. So we'll go through all these and make sure that you're on the right track for these. Question 1 and 2 are pretty straightforward, actually. We want to add these vectors together. The total vector here would be, what, just 250 meters. Right? This is, honestly, adding the vectors together in question number 1 is just like adding vectors together like you did in grade 1 or grade 2. You just didn't call it adding vectors together. Right? When you added 3 plus 4 and you got 7, you were really adding plus 3 plus positive 4, or sometimes 3 to the right, 4 to the right, giving you 7 to the right. You just didn't think of it as adding vectors together. It's exactly what we're doing right here. Now, number 2, this is a little bit harder. You didn't do this in grade 1. When we're adding 150 to the right and 100 to the left, or 150 plus negative 100, that gives us positive 50 meters. That was more like, I don't know, grade 5 or grade 6 vector addition. Again, you still didn't call it vector addition, but that's what it amounts to when you're adding a positive and a negative together. Question number 3, I'm not sure when you started doing the Pythagorean theorem. In other words, grade 7? In other words, when you started adding vectors in 2 dimensions together without realizing that's what you were doing. And we have, in question number 3, a vector diagram drawn, and it is a right-angled triangle vector diagram, which is always the goal. That's where we want to get to, is a right-angled triangle vector diagram. If that's what we got, then all we got to do is find the hypotenuse of that vector diagram. Is this vector diagram drawn correct, by the way, all 3 vectors, including the one that I just drew in? Hayden? Yeah, this is drawn head to tail, right, which is what it should be, and the final one, the resultant vector, which is, it said add the vectors together. When we add vectors together, we get a sum. The resultant vector is the sum of the vectors. So whatever that number is, whatever that hypotenuse is the sum of all the vectors. That's the answer that we're looking for when the instructions say to add the vectors together here. This is drawn correct. Okay, that resultant vector is always drawn from start to finish, tail to tail, head to head. All right, how do we find that resultant vector? Well, that's the equivalent of C, right? So a squared plus b squared is equal to c squared, or a squared plus b squared is equal to r squared, or r is equal to the square root of a squared plus b squared. So we're going to say it's 10 squared plus 20 squared, square root. Okay, that gives us a value of, let me move this over here. Let's say square root of bracket 10 squared plus 20 squared. And that bracket gives us a value of 22.4. It actually should be 2 digits, right? So 22 meters. Are we done with that, though? No, if we're adding vectors together, what do we get? A vector or a scalar? If we're adding vectors, we get a vector, right? And vectors require magnitude and direction. So how do we find the direction? Well, we label an angle. We label the angle at position 1, position 2, or position 3. Position 1, because we always draw that angle at the start of the vector diagram, right? Now, let's use the 10 and the 20 here. We're looking for theta. Let's use the 10 and the 20 to get the theta. Which side of the triangle is the 20 here? Is that opposite, adjacent, or hypotenuse? It's the adjacent. Which side of the triangle is the 10? Opposite. So which trig function are we going to use with opposite, adjacent, and hypotenuse? Sorry, opposite, adjacent, and theta? Tangent. Theta is going to be the inverse tangent of opposite over adjacent. So we're going to say on our calculators, remember what we do on our calculators the first time? First time, not like every day, but the first time every day that we're using an angle, right? Up until the last few days, we haven't been using angles, so we didn't need to do this. It doesn't matter what mode we're in if we're not using angles. But if we're going to do something with a trig function, with an angle, then we better make sure we're in degree mode. What's that little trick that we do first? Yeah, the first thing we do is hit sine 90. And we get, ooh, 0.89. What's it supposed to be? It's supposed to be 1. Means I'm not in the right mode, right? Yeah, I'm in radian mode. I switched it this morning to radian mode on purpose, by the way, just so that you'd see what we get when we're not in degree mode. We're in radian mode. We do sometimes in math class use radian mode, sometimes use degree mode. So we want to make sure that we're always doing that check when we're coming to physics class to make sure that we're in the right mode. So let's go to mode, go down here, over to degree. Okay, now let's clear it. Let's just hit it again now to make sure that we did it right. Okay, there we go. So now we're in degree mode, we're good to go. Let's say now theta is the second function tan of 10 over 20. Gives us a value of 26.5 degrees, or we're going to say 27 degrees. Now, how are we going to express that? 27 degrees what of what? Remember the analogy I used? I'm 2 meters from the front of the room. I'm 6 meters from the back of the room. Which one is it? Is it 27 degrees from, we're going north and east here, right? Is it 27 degrees from the north, or is it 27 degrees from the east? Where are we measuring that angle from? It's measured from the east, right? It's touching the east. So it's from the east. But yet we're going north from the east. So we're going to call it 27 degrees north of east. North from east or north of east. Good? Good? All right, number 4 is real similar to that. Number 4, is this a good vector diagram so far? It's not complete, is it? But is it good so far? Yeah, it's drawn head to tail. That's good. The resultant vector is going to be drawn from start to finish. Is this a good one now? What's wrong, Cam? Yeah, I'm missing the arrow. I got to put the arrow in there. That's important, right? That's important so that we can get that direction down right. And it's going from start to finish. That looks good. We're going to draw our angle where? Position 1, 2, or 3? 1, 2, 3. Yeah, it's position 3 there, always at the start of the vector diagram. Good. And we're looking for the value of r. The question could say, find the resultant vector. It could say, add the vectors together like it did here. It could say, find the sum of the vectors. It could say, find the displacement, because that's the total displacement is the sum of all those displacements, right? There's all kinds of ways that we could ask that question. It boiled down to exactly the same thing. We find the value of r by doing the square root of 15 squared plus 10 squared. Okay, and that's going to equal, let's figure that out here. Square root of 15 squared plus 10 squared, and that bracket, we get a value of 18. And we're going to find theta by using which trig function? 15 and 10. The 15 would be which side of the triangle is it? Michael, which side is it? Okay, Michael. That's okay. Ben, what is it? Yeah. And Michael, the 10 would be, all right, right. So if we've got opposite adjacent, we're going to use tan. The inverse tan of 10 over 15. We don't need to do that check with our calculator again. We know we're in degree mode. We haven't switched it. The inverse tan of 10 over 15 gives me a value of 34 degrees. And how do we express that? 34 degrees what of what? But we're going south and we're going east, right? Are we going south from east or east from south? In other words, where are we measuring our angle from? Are we measuring it from the east or from the south? Okay, so it's going to be south from east then, right? Or we'll call it south of east. Good? Is that okay, everyone? All right. Let's do question number 5. This is drawn correct, head to tail, resultant vector drawn right there. Good? Find the sum of these vectors, find the resultant vector, find the displacement, add the vectors together, all the same thing. We're looking for theta here. Is that drawn correctly? Is that the right spot? Yep. Yep, it is. So let's find the value of r. The magnitude of it is 5 squared plus 10 squared. Square root that. Second function of bracket 5 squared plus 10 squared gives me a value of 11.1, or we'll just call it 11 meters. Two significant figures. And theta, which trig function is it? Yeah, you start noticing some patterns here, right? Like when we're looking for that angle, it ends up always being tan. It does. We just want to know why it's tan, though. I'm not saying that it's not okay to remember that. It is okay to remember that we're always going to use tan here. But it's also important to understand why we're using tan, so that if you do find yourself, sometimes we get a test, and like we get partway through, and it's like you start panicking a little bit, right? Like I don't remember this, and I don't remember that, and just because we get nervous, we want to understand things so we can always fall back on figuring it out if we don't remember it, right? This is tan because we have opposite and adjacent. So theta is the inverse tan of 5 over 10. Theta ends up being equal to 27 degrees. And we're going to say that's 27 degrees east of south. What is it, Xander? Yeah. South of west. Good. South of west. We're measuring it from the west, but it's south from the west. Good. Two more. And these two more are a little bit harder because these two, questions 6 and 7, we got a vector diagram here, right? 6 is a vector diagram, and I can draw my resultant vector from start to finish. That is absolutely okay. But we don't have a right angle triangle, and that's the goal. Get a right angle triangle, because with a right angle triangle we can use some trig and we can use the Pythagorean theorem, right? So let's get that. Remember what we got to do. First thing we got to remember is show your work, right? Don't just get numbers, show your work here. So for number 6, the x component of the first vector, how much of that 10 meters is x component? All of it, 10 meters. How much of that 10 meters is y component? None of it. The next one, 5 meters. What is the x component of the 5? Yeah, it's 0. And the y component of the 5 is 5. How much of the 15 is x? All of it. How much of the 15 is y? None of it. Whoops. So let's write down none of it then. 10 plus 15 is 25. 5 plus 0 plus 0 is 5. This is where some people stopped on their homework because they're like, well, I added those vectors together, right? No, I've partially added them together, but the sum of the vectors is this, 25 and 5. We still have to find this resultant vector that goes from start to finish here. That r, along with that theta, is the sum of those vectors. Does that make sense? So another time, right, like you made a mistake, you ended right here, that's fine, okay, you were confused about it, that's fine. That's what homework is for, right, is to clear up that confusion. But on the quiz or a test, don't stop here, because you're not going to get very many marks for that, right? You got to go to this step and find the value of r. R is square root of 25 squared plus 5 squared. What does that work out to be? Does anybody have it? 25.5 or 26 meters, okay, and theta would be the inverse tan function of 5 over 25. That's going to be a pretty small angle, isn't it? And what did you get there? 11.3. We're going to round that to 2 digits, or 11 degrees. And what's that going to be? 11 degrees. 11 degrees what of what? Not east of north, no. We're going to make it north of east. Does anybody else agree with that, 11 degrees? Yeah? It's north of east there, Marshall, because we're measuring our angle from the east, right? Of the east. Yeah? Okay, so if you did the y component first, So then you're going to get 5 and 25. That is perfectly valid. But your resultant vector here is going to look like this. It's going to look the same, right?
Yeah.
That resultant vector looks the same, except when you calculate the angle, it's going to be inverse tan of 25 over 5, right? Which is going to give you, this is my lightning fast trigonometric calculations in my head here. It's going to give you a value of 79 degrees. But that would be 79 degrees east of north. It was my lightning fast in the head calculation, but it wasn't trig that I did. What was my lightning fast in the head calculation? 90 minus 11, right? Okay, that one's a pretty easy one to do. Does that make sense? So is that what we got? Good. So both of those are correct, 100% correct. Doesn't matter which way you draw. I tend to always go X and Y, but there's no good reason for that. It's just habit. Finally, we got one more here. It was question number 7. We do it the same way as we did number 6. Our resultant vector, this is good, right? Head to tail, head to tail, head to tail. It's all good. The resultant vector, or the sum of the vectors, is this one right here. But we want a right angle triangle. That's the goal, right? So let's get a right angle triangle by doing our x components and our y components. What's the x component of the 8? Yep. What's the x component of the 8? Anybody? Miranda, how much of that 8 is x? Good. And how much of it's y? Yeah, we're going to make it negative 8 because it's downward, right? How much of the 12? How much of the 12? Aaron, how much of the 12 is x component? How much of that 12 is x? Yep, all of it, 12 meters. How much of it's y? Good. How much of the, Brent, how much of the 10 is x? Good. How much of it's y? Right, so it's positive 10 because it's up. Let's say how much of that 4 is x? Good, negative 4. Okay, it's important to get that negative right. And how much of it's y? Good. Yeah, question? Oh, yes, yes. Yeah, you're right. That is absolutely correct. That should be drawn the other way, yes. So from start to finish. Good. Thank you for that. So we add these up. 12 plus negative 4 is 8. Negative 8, 10 is 2. We're going to redraw it with an 8 and a 2. Or, Sawyer, you could have redrawn it as a 2 and an 8, right? Either way. And then our resultant vector, which is the sum of the vectors drawn from start to finish. By the way, what do those little vertical lines mean? Absolute value. In other words, when we solve for the hypotenuse there, we're not getting the direction. We're just getting the absolute value of it, the magnitude of it. The direction is going to come from the angle, right? Nia, where am I going to put my angle? Position 1, 2, or 3? Yes, always at the start of your vector diagram, right? What's this going to work out to be? Like probably 8.1 or something like that, is it? 8.1, 8.2? 8.25? So 8.3 then? To 2 digits, right? And theta is the inverse tan of opposite over adjacent. What's the opposite side here? The opposite side is 2, the adjacent is 8. That's going to be a relatively small angle, I think. The inverse tan of 2 over 8, what does it work out to be? What is it? 14. And what are we going to express that from? Is it measured? Well, we're going north and east, right? Going north and east, is it measured? Ryan, is it measured from the north or is it measured from the east? Sorry? Yes, it's measured from the east, so of the east, north from east or north of east. Good. So let's do another example here now that it kind of combines what we've done over the last couple of days. This is a vector addition problem clearly where we have these solid line vectors that we're adding together to get our resultant vector, which the way that I have it drawn is my dotted line vector. This is drawn correctly, right? This is drawn head to tail, that's fine. And then the resultant vector that we have right here is drawn from start to finish. That's all good, right? The problem is, I can't really find the sum of these vectors. I can't really find the resultant vector. I can't really add these vectors together. I can't really find the displacement of this right now because I don't have a right angle triangle. And it's not as easy to get a right angle triangle as it was in questions 6 and 7 in your homework last night, because I got this angle 30 degrees. Listen carefully. Going forward in Physics 20 and in Physics 30, whenever you see an angle like this, whenever you see an angle that is not 90 degrees or 0, whenever it's 30 degrees or 50 or 60 or 27 degrees, I want you to think 5 words. I want you to repeat after me. I don't like funny angles. Say it. I don't like funny angles. All right, so we got a 30-degree angle here. I don't like funny angles, so what I want to do is get rid of that 30 degrees. If I don't like funny angles, then I want to get rid of the funny angle. So I have to take it off to the side and resolve it. And this is work that you're going to show, right? I always want to see this work. Redraw this 15 meters. It doesn't have to be perfect. And the 30 degrees right here. Label an X and a Y. We've done this before, right? We found the X and Y components of vectors like this, just not all together in one of these problems. So let's find the X value. The X value. Which side of the triangle is the X side? Is that opposite, adjacent, or hypotenuse? Adjacent, and the 15 is hypotenuse, right? So if we want to find the adjacent side, the X side, we're going to say which trig function? Adjacent and hypotenuse. Marty is what? Adjacent and hypotenuse goes with? Cosine. Good. So cosine 30 degrees is equal to adjacent over hypotenuse. That works out to be, I forget, off the top of my head, 15 cosine 30 gives me 12.9904. And now we can find the y component by saying sine. It's the adjacent side, sorry, the opposite side. Sine 30 is equal to opposite over 15, or y is equal to 7.5. This is what we did a couple days ago, right? Found the x and y components. And you might have wondered, like a couple days ago, well, why are we doing that? Why are we finding an x component and a y component? Well, it's so that we can find the sum of all the vectors. That's the end goal. This was the tool that we learned, and now we're putting it all together here. By the way, when I do that, I like to box it off like this. We don't have to, but I like to box it off like that. Reason being, if I always do that, if I always structure it this way, if I always put a little box around it, then it builds familiarity and it builds comfort, right? I'm in the middle of that test and it's like, yeah, I'm a little bit stressed because I had trouble with the last question. I get to this question, there's comfort in having a way that we always do it, right? So I always box it off. I always do it the same way. Now, what I do here sometimes, you don't have to do this, but some people really like to do this. What we can do is say, well, look, this 15 is dead to us, right? Like it is dead to us. We never want to see that 15 again. So let's replace it with 12.99 and 7.5. And then let's just scratch this out. So instead of having a 15 meters, we have a 12.99 and a 7.5. And now this question looks a lot easier, doesn't it? Now this question looks just like questions 6 and 7 that you had for homework, doesn't it? The only difference between this question and questions 6 and 7 that you had for homework is that we had that funny angle. What do? Well, we don't like funny angles. So we broke that funny angle up into an x and a y. And we just turned it into a question like number 6 and 7. Now, we still got a ways to go, because we still got to add up the x's and the y's and then combine them, but at least we're not dealing with funny angles anymore. Okay, what's the x component? What's the x component of the first vector of that 10? 10 meters. What's the y component of it? 0. What's the x component of the 5? 0. What's the y component of the 5? Negative 5. Jack, you said negative there? Yeah, good. Negative because it's? Good, because it's down. What's the x component of the 15? Remember, the 15, we're never going to use that 15. It's dead to us. Once we resolved it into x and y, it's gone forever. What's the x component of the 15? 12.99. And what's the y component of 15? 7.5. Don't ever put in 15 there. Okay, it's gone forever. Let's add these up. 10 plus 12.99 is 22.99. 0, negative 5, 7.5 gives me 2.5. We know what to do with this, right? We got 22.99 to the right. How do I know that's to the right? That should be 9904 actually, right? Yeah, it's positive, and it's the x component, not the y component. It's the x component, and it's positive, so it's to the right. The 2.5 is up because it's positive. Is that drawn correctly? Head to tail, right? Head to tail. The resultant vector is drawn from start to finish. Does that resultant vector look like the resultant vector that I drew up here? Yeah, pretty much. It's not quite perfect, right? Because my scale isn't perfect, but it's close. And theta is, where's theta going to be here? Tegan, where's theta? Position 1, 2, or 3? Good. Always at the start of the vector diagram, right? R is the square root of 22.9904 squared plus 2.5 squared. So the magnitude of the resultant vector is 12. Oh, let's do this. 22.9904 squared plus 2.5 squared. Don't forget to square root all that. 23 point, let's call it 23. And theta is the inverse tan of opposite over adjacent. What's the opposite side of the triangle here? If I take a look at this triangle right here, the 22 and the 2.5, what's the opposite side of the triangle? Is it 22 or 2.5? Good. So it's the inverse tan of 2.5 over 22.9904. That gives me, that's going to be a really small angle, isn't it? Because my rise there isn't very much at all. The inverse tan of 2.5 over I get 6.2 degrees. What would that be? 6.2 degrees north of east. Good. Or you could have got, what, 84 degrees east of north? It would have been the other one. Good? All right, what I'd like you to take a look at now at your desks is worksheet number 7, questions 8, 9, and 10. Worksheet number 7. Oops, wrong one. Number 8, 9, and 10. Okay, I want to do number 8 here. We're just adding two vectors together here. If we draw a resultant vector here, we've got a triangle already, right? But it's not a right angle triangle. Some of you say, well, I can solve this. Like I can do this from this. I don't want you to do it straight from there. I want you to do the x components and the y components because it helps develop an understanding that's a little bit better. And it's so important to understand this, to understand what we're doing. If you don't completely understand it quite yet, that's okay. That comes through practice, right? But this is probably, I would say, of all the things that we do in Physics 20, this is the thing that carries through the most to everything that we do in Physics 20 and Physics 30. Like vector addition, not displacement vector addition. Sometimes it's momentum vector addition and force vector addition, but vector addition like we're doing here now carries through to many parts of Physics 20 and many parts of Physics 30 for that matter. So we want to make sure that we can't just do it mathematically, we want to understand it mathematically, and doing the components is an important part of understanding it here. All right, so let's get rid of that 30-degree angle. I don't like 30-degree angles. I don't like any funny angles. So let's get rid of it. Let's just draw it off to the side here. Let's make this one my x, this one my y, and then let's find the value of x and y. We can find x by using cosine. Cosine 30 degrees is equal to adjacent over hypotenuse. I think it's 32.9904. I think that's what it was. And the y component is, we'll say sine 30 degrees is equal to opposite over hypotenuse. And that's going to be equal to exactly 20 meters. And I'm going to box that off. Why? Because, well, that's what I do. There's no special reason why I have to, but I do it the same way every time. I just want to be the same every time, and that makes it easier come test time to remember what to do. All right, now if I want to, I can draw in a little 32.9904 right here and a 20 right here. By the way, that actually should be negative 20, shouldn't it? Whether you label the negative right there or not, it's not a huge deal as long as you recognize it's down. I'm going to scratch this out. That 40 meters is dead to me. I never want to see that 40 meters again. What's the x component of the 80? What is the x component of the 80? Check. How much of that 80 is x? Yeah. How much of it's y? None of it. 40 meters. We don't want that 40 meters, right? How much of the 40 meters, Beth, is x? Yep. 32.9904. And how much of it's y? Yeah, except we'll make it negative, right? Because it's down. 112.9904 and negative 20. Combine these. 20 down. That's correct, right? Head to tail. Does that resultant vector look the way that it should? Yeah, it looks the way that the first one did, right? Except it's simpler because now it's a right angle triangle. Where am I going to draw my theta here? Position 1, 2, or 3? 1, 2, or 3. Kevin, where am I going to draw it? 1, 2, or 3? 1. Good. Start of the vector diagram. Good. So R is the square root of 112.9904 squared plus 20 squared. Gives me a value of 114.74. We're going to round it to 2 digits, actually, so we're going to make it 1.1 times 10 to the 2. And theta will be the inverse tan function of, what's my opposite side here? What's my opposite side? And we're not done here, okay? What's my opposite side? Tegan, what's my opposite side? Is it 112 or 20? The opposite side of this triangle, 112 or 20? Good. So it's the inverse tan of 20 over, what do we get there? Gives me an angle of 80 degrees. And we're going to say that's 80 degrees, what of what? Alex, what's that 80 degrees, what of what?
South of east.
Yeah, we're measuring it from the east there. The angle's touching the east. So it's going to be 80 degrees south of east. We had to do it the other way. It would have been 10 degrees east of south, right? That would have been fine, too.